Good afternoon. Can everyone hear me? Okay. My name is Peggy Jenkins. I manage the Indoor Air Quality Program here at the Air Resources Board. And unfortunately, Bart Cruz, our division chief of the research division, couldn't be here right now. He will be here shortly, but he asked me to go ahead and introduce Dr. Smith. Before I do that, I have one announcement. For those who are viewing this on the webcast, we'd like to encourage you to send your questions to during the Q&A session at the end of the presentation to sierrarm@calipa.ca.gov. That's SIERRA@calepa.ca.gov, and that will show up on the webcast screen as well. So with that, it's definitely my great pleasure to introduce Dr. Kirk Smith. Dr. Smith is Professor of Global Environmental Health in the School of Public Health at the University of California at Berkeley. Dr. Smith also is the founder and director of the campus-wide master's program of the East-West Center in Honolulu. His research and policy work focuses on environmental health and climate issues in developing countries, particularly those related to household air pollution and energy. His work on climate focuses on co-benefits, that is, strategies that achieve both climate mitigation adaptation goals as well as providing immediate local benefits such as increased health protection and other improvements. Dr. Smith's recent activities include participation in the Intergovernmental Panel on Climate Change, the National Research Council's Advisory Committee to the U.S. National Climate Science Program, senior advisory committees on climate change research strategies for the National Institute of Environmental Health Sciences and the Global Review of the Institute of Medicine, the Board on Atmospheric Sciences and Climate of the U.S. National Academies, and organizer of the 2008 Annual Reviews Symposium on Climate Change and Health. Dr. Smith has been a member of the National Academy of Sciences since 1997. And I'd like to add that I've known Dr. Smith for many years. He's been just a truly key protector of public health, not only for our nation, but for many developing countries, and a true leader in this field. Today, Dr. Smith will discuss carbon on steroids, the untold story of methane, climate, and health. Please join me in welcoming Dr. Kirk Smith.
Well, thank you, Peggy. It's always a pleasure to come here. This is the center of the action, as you know, in the world in terms of air pollution. I think there are more professionals working on air pollution issues here than any other agency, perhaps even than the national agency in the U.S., and certainly than any other country, probably more total than any 50 countries you wanted to choose. And, of course, now with the climate change portfolio, you're really, I'm sure, running scared, but also it's exciting time, particularly after last week, for all of us in this regard. Now, I'm going to talk about methane, and I'm going to specify what I'm not going to talk about, but I'm going to talk about a kind of global view of methane. And it's designed to be provocative, but I hope not too much so. But nevertheless, I expect that it will be provocative for some people. Now, this is the version of the title slide that I would show my mother. But just to be, a bit more accurate here, I was just one of 2,000 scientists after Gore took his cut of 50%. The rest of us got. But I will be using a lot of material from the fourth assessment of the IPCC. And in fact, it's great to have this material because some of the things I'm going to show you you might think is quite controversial if I showed my calculations for them, but at least I can show the IPCC. And if you're interested in this field and haven't spent a lot of time on the IPCC website, I recommend it because it's a very good website. It's got a lot of good material, a lot of good references, excellent, the summary for policymakers, summary for technical people, the full reports. You can download all the figures and tables easily and so on. Okay, so first thing, having done this before, I know that some people get very upset that somehow I'm not that I don't believe that. This is very true. Don't think otherwise. But I'm not here to talk about carbon dioxide. Now, I'm here to tell the methane story. Now, there are 5. You remember methane is, this simple molecule, 1 carbon, 4 hydrogens. When it oxidizes or burns, it creates water and carbon dioxide. But there are 4 sides, the subplots to this. One is the methane and global warming. Another is methane and global health. Another is methane and the health of the poor. Methane and global equity. And methane and history. Now, obviously, you don't have a lot of time to talk about any one of these things, so I'm going to move through things pretty fast, but we can get to questions afterwards. And what I am not speaking about is particular methane reduction possibilities in California. When this announcement of this seminar went out, I was deluged with emails from people who have very particular interest in this, but I'm not an expert on this. And I'm not going to talk about other very important issue, which is the potential for runaway methane emissions as positive feedback in global warming, from the tundra or the Arctic sea bottom or whatever. Another important issue, but not what I'm talking about. All right, you remember methane. It's one of the 3 major greenhouse gases. We talk a lot about CO2. We see how it's, risen dramatically in the last 100 years or so, but so has methane. Of course, so is N2O. So I'm going to be speaking about this methane, and at the end, I'm going to talk a little bit about the historical side of it. One interesting thing about methane is we influence the global cycle much more than we do actually with CO2. Actually, 2/3 of total emissions today are from human activities, only 1/3 from natural activities. So in that sense, we influence the global cycle more. It also means there's bigger variation as our activities go up or down. The atmospheric levels tend to go up or down, also influenced by the shorter lifetime of methane. And in recent years, as many of you may know, the methane levels in the atmosphere have been more or less stable. They just vary by season. But in last year or this year, they were starting to rise again. The estimates are that emissions are going to continue to rise. The atmospheric levels are a function of emissions, of course, but also other things, and what's happening in the natural world as well. And the rate of emission growth is similar to CO2, expected. Now, this is one of these graphs I mentioned from the IPCC, and it's, in some sense, the central thing I'm talking about here. This is the warming, basically today, 2005, from all human emissions since 1750. So this is the unit that's used, watts per square centimeter, per square meter. And there are a lot of different pollutants there, not all gases that affect this, but at the moment I want to focus on these first 2 lines. And you can see that CO2, right now, up there, CO2 is the biggest thing that's causing warming. But methane, which is this entire bar here, across here, here's the methane bar, is a significant fraction, in fact 55% of the CO2. So it's not a small actor, even compared to the gorilla in the closet, which is CO2. You'll notice also that some of that impact is from the methane directly, the direct warming potential of the methane in the atmosphere, but also from the tropospheric, the T is for tropospheric, ground level ozone that's created by the methane, which is also a powerful greenhouse gas. In addition, methane, what does it change into? Well, it changes into water and CO2. So some of the signal from methane is due to its decay products, if you like, its combustion products. So it is a significant component of what's happening in the world and what's happened to us. We'll get back to that. So methane is a much more powerful greenhouse gas per ton or per molecule than CO2. It's partly due to its direct effect, but also because it creates ozone. Nearly 100 times, if you use mass as the unit, the metric, it's about 100 times worse than CO2 as warming, about 3/4 of that from its direct effect, the rest from the ozone. It eventually, of course, turns to CO2, and if you're using this mass unit, it creates 2.7 times more tons of CO2 per ton of methane. And that's contributed a significant amount to global warming, as you can see. But it does have a shorter lifetime, and therefore you can't treat it equally to CO2. And this is the nub of the problem that I'm going to talk about here, is the sort of the temporal perspective that we need to address if we're going to come to a way of dealing with a mix of pollutants that we have in global warming. So let's look at the math of methane decay, of the greenhouse gas decay. This is from the fourth assessment now. CO2 goes into 4 compartments. There's 19% of it goes into a compartment with a very short lifetime, a year or two. Another third goes into a compartment with a fairly short lifetime in the atmosphere, and 26% goes into long-lived lifetime, and then 21% or so has a very long lifetime. Methane has a quite different temporal relationship. It has basically treated as a 12-year lifetime. By lifetime, this is really an E-folding time is the proper term, 1 over E, to reach 1 over E. It's not a half-life. The half-life for methane is about 8.5 years. And it decays away faster overall. But in the short term, CO2 actually decays faster. This is what it looks like the first 10 years. For the fraction of remaining 2008 emissions, you can see, because of the short-lived components of the compartments that CO2 goes into, it actually decays away faster than methane initially. And then, of course, the methane is disappearing and that much of the CO2 is remaining. Over a 100-year time perspective here, you can see that little stuff right at the beginning, but basically there's hardly any of the methane left and still much of the CO2 left after 100 years. If we look at it on a relative global warming basis, that was just on a per ton basis. This is global warming, including the instantaneous warming potential of the methane. And I had to put this on a log scale, otherwise you can't see much. You can see that it takes actually not equal warming for a ton of methane with the CO2 in 2008 until the year 2075. They'll be producing about the same warming. And the integrated warming over that it takes that ton of methane, it takes 5,000 years for a ton of methane to equal the total, the ton of CO2 would equal the total warming of the ton of methane, even though there's a short-lived, the methane is shorter lived. So much more powerful in its, that while it's there, it's causing a lot of warming. There are actually 2 types of methane. There's biogenic methane from animals and biomass combustion and landfills and so on. The CO2 it creates is renewable. It doesn't add to the atmospheric load of CO2. And then there's fossil methane from natural gas, coal mines, fossil fuel combustion, and so on. The CO2 it creates does add to the global total of CO2. So if you're really going to be picky, you need to treat them differently. The global anthropogenic methane emissions in 2005 are estimated to be about 305 million tons, and they're distributed like this, and you can see about 25% of it is fossil methane from the leakages from the oil and gas industry, coal mining, fossil fuel burning, and so on. And then the rest of it is biogenic methane, much of it from livestock and rice production, but a lot of it from waste. In fact, if you look at this, the big ones are agriculture, that's the rice and the livestock, poor waste management, that's the manure, landfills, and wastewater, and leakage, that's from the fossil fuel industry. And these are important distinctions. None of these really relate, except potentially the livestock and rice production, relate directly to human welfare. They aren't, to make changes in these things doesn't require people changing their lifestyles. Let's leave the livestock out. Fixing leaks, doing better with waste disposal are things that can be done without major disruptions in social fabric of things, unlike a lot of the things we need to do with CO2. So I would argue that this is, in a sense, low-hanging fruit. These are things that we can do fairly quickly with not too much political difficulty, some cost, of course, but in ways that are a lot easier while we're learning how to deal with CO2 in the long run. All right, so if you were to look at this, the fossil methane curves, they actually never cross because the methane that changes, the fossil methane changes into fossil CO2, and so it adds, and so it's always greater than the CO2. So in this case, if those other curves I showed you were actually for biogenic methane, this is actually fossil methane, that doesn't cross CO2. So if we look at global methane emissions, with these lifetime, these decay functions associated with it, you can see that actually this year there's the immediate impact of global emissions is greater for methane than for CO2. About, I don't know, what's that, 18% greater. And instantly goes up because the methane, the CO2, this is the ratio here, the CO2 is decaying faster, part of it. And it goes up to about 20%. And then over 20 years, it goes down to about 40%. But notice that in that 20 years, the global methane releases in 2008 will create 84% as much warming as the CO2 in the next 20 years. Now, that's a rather significant fraction. And I ask you if the discussions on global warming that you see in the newspapers and discussions, even technical and policy discussions, recognize the relative importance of methane in this regard. So how do we compare projects to reduce different greenhouse gases? Why not take all future warming, and it's 5,000 years before methane equals CO2. Of course, this would mean take no effort would go into avoiding emissions of the shorter-lived greenhouse gases, such as methane and black carbon and things like that, because CO2 has such a long lifetime. It would result in spending money to protect people thousands of years in the future, while, if you only have a certain amount of money to spend in a balanced way, spending less to protect people in the short term. The IPCC established in '96 the official global warming potentials to deal with this problem, which are weighting factors to compare the impacts of different greenhouse gases. They're built into the Kyoto Protocol, the Clean Development Mechanism, all national inventories and reduction plans, including those, as far as I could see, from those used in California. The current official global warming potentials are based on a 100-year time frame. They look out 100 years. And in that, methane back in '96 was calculated to be 21 times worse than CO2 by weight. Actually, the newest assessment says it should be 25, and probably may be changed in the next round of negotiations. This is equivalent to a 0.75% discount rate, if you are familiar with that term. We'll talk more about that in a minute. But for making decisions on how to spend resources when impacts are upon us, and remember, the world, our thinking about climate change is quite different than it was in 1994 when these things were developed by IPCC. Climate change in those days seemed very far off and theoretical. We weren't even sure, we're less sure that it was even going to be happening. And certainly there was no clear evidence that it already started happening. We're in a very different situation today. And even if you think that these very low discount rates, this very long time perspective might have been appropriate in 1994, and I think there are arguments, one could argue that today, where you say hardly a few days go by without hearing about another effect of climate change on the human or natural environment, whether that long perspective is any more suitable. The IPCC published another warming potential based on a 20-year perspective, which has a weighting of 72. This is equivalent to an 8% discount rate, which is fairly similar to what people use in financial investments, for example. Some of us are proposing something in between as a more appropriate weighting for methane, roughly around a 3% discount rate, which is the kind of thing used for long-term investments in international health and other arenas. And that would be equivalent to a global warming potential of 48. Let me show you that. So how does that work? Well, I showed you this log thing, but it's hard to do this on a log basis, so I'm changed it to a linear one. So the 20-year perspective basically says we take the ratio of the area under this methane curve and compare it to the ratio of the area under the CO2 curve, which you can hardly see at the bottom there. And that is actually 72. But a 100-year perspective says, and then we don't count anything after that, after 20 years. The 100-year perspective basically does the same thing except out 100 years. So you take the area under that methane curve and compare it to the area under the CO2 curve, and that's according to the recent assessment, a factor of 25. Now, I don't want we can talk more about this framing of the question in terms of time horizons, which I think is actually fairly perverse, as opposed to discount rates, but this is how it works. Well, if we look at equivalent discount rates and methane global warming potentials, the current official potential of 21 gives you a discount rate of equivalent to 0.75%. At 25, it's equivalent to about 1%. And as I mentioned, somehow it got left off here, a 3% discount rate gives you a global warming potential of about 48. Here's the you can invert it another way. You can look at the equivalent global warming potential at different time horizons, and the 3% discount rate, global warming potential of 48, is equivalent to a 40-year time horizon, if you like that formulation of time horizon. So it's basically saying that we can't afford to be spending money on people 80, 90, 100 years from now when we've got things that are happening now and we need to protect the current generation, ourselves, and our children. Or, I want to put it more selfishly, if I want to make an impact on global warming in my lifetime, I need to think a lot about the shorter-lived components, and of course methane is the most important of them. All right, it does make a big difference. The IPCC did publish looking at all the pollutants on a 100-year and on 20-year perspective. And here's the 100-year, the standard perspective, and here's CO2. And methane, this is all. This is basically the amount of emissions in the year 2000. Consider it today, basically, 100 years forward. And CO2 is the most important. Methane is still quite important, but definitely second to CO2. But if you take a 20-year perspective, which they've shown here also, methane is actually more important than CO2 over the next 20 years. So it does make a big difference in how much you might spend or how much you might value or judge one mitigation strategy over another, CO2 versus methane in this case. Of course, it also has implications for the other pollutants. All right, summary of the first story. Much more powerful greenhouse gas. You saw all that. Shorter lifetime, thus changes in emission rates with a much faster impact. Jim Hansen, probably the most well-known climate scientist, says all the time, if you want to make an impact in the next 20 years, then almost nothing you can do with CO2 is going to make a difference. You have to work on the short-lived components. Black carbon, I know a lot of interest in, but methane is another one. But it also means there's going to be a lot more variability in the system. All right, methane and global health, my second thing. Well, the increases of wide-scale tropospheric ground-level ozone is becoming a major world problem. Significant health-damaging pollutant, as you know, damages also ecosystems and agriculture. And methane emissions, I think many people don't understand, are the primary cause globally. Not necessarily in any particular urban air basin like Los Angeles, but globally, methane emissions are the primary driver behind the rise in tropospheric ozone. Therefore, reduction in methane emissions will have a benefit for health directly. You know the simple formulas here for urban ozone creation, interaction with the nitrogen oxides and volatile organics, but the global one is mainly also has methane, and methane globally, not necessarily in any one place, not necessarily in California in any particular place, but globally, methane is the primary driver. Analyses that are done, here's showing the rise in tropospheric ozone on the left, what the world might look like in 2100 if things keep on going in terms of ozone levels. This is separate from urban levels. Some studies done by Jason West at University of North Carolina and Denise Mazzarella at Princeton looking at the cost effectiveness of control. And their work shows that probably the most cost-effective way to deal with this ozone is the methane reduction, even in spite of the fact that the nitrogen oxides are important players as well. Here they've calculated the effect of a reduction of 20%, or about 60 megatons of methane. Globally, the effect of the changes of the methane, the ozone levels. And then here they've also calculated mortality changes as a result. So I don't want to get into the details of that unless somebody wants to ask, but the summary is methane is a precursor to tropospheric ozone. Ozone levels are rising around the world. Significant impact on ecosystems and health, and agriculture as well as health. And as you may know, as WHO and other agencies, including CARB, look at ozone and the new evidence on the health effects of ozone, the pressure is to lower the, to make the standards tighter and tighter. I was on the WHO committee that looked at this, and it was an awkward thing because what you'd like to set the standard at in terms of the health information is right about the levels of background levels that are occurring in Europe and other places. So there, you might say there's no place to hide now. background is down at the level we have pretty good evidence for health effects. So this is not an inconsequential health impact. Now I'm going to get into the third issue, which is methane in the poor. Here's the world energy picture. Sometimes forgotten that 9 or 10% of world energy use is actually in traditional biomass use, which is mainly in households in the third world. Here's from the IPCC. I know you can't read that, but that big, this is the biomass flow cycle, biomass energy flow cycle in the world, and that big block at the top is household fuels in the third world. That's dominates this this fuel. This is an estimate of the percent of households using simple solid biomass fuels for heating, cooking, and heating in some cases. About half the world's households. Well, when you burn these fuels in a simple stove, you get very incomplete combustion, and one of the major components of it is the emissions of methane. You also get emissions of various other hydrocarbons and carbon monoxide and black carbon and PM 2.5 and so on, but you get a significant amount of methane as well. Indeed, if you just look at Indian stoves, based on the measurements of emissions from different categories of fuel and stoves in India, that about 2 million tons of methane are released every year from Indian stoves of the 300 or so million tons total global emissions. Not a small fraction. Now, small amount from each stove, but not a small fraction overall as a sector. Similar for Chinese stoves. In addition, of course, these stoves produce, as I mentioned, a number of other noxious pollutants. In fact, I call this a toxic waste factory. It takes a perfectly benign material, never would, just has carbon, hydrogen, oxygen in it. You can eat it, doesn't hurt you. And because of the incomplete combustion, these products of incomplete combustion, which are typically 8, 10, even 20% of the fuel carbon goes off as those products of incomplete combustion instead of CO2, complete combustion. And almost every one of those is toxic, except the methane, which is not directly toxic, but does add to ozone levels. And am I exaggerating? No, I don't think so, because this is the set of materials that you find in wood smoke. And, you know, there are thousands of things. It's in some ways very similar to the most well-studied biomass smoke in the world, which is tobacco smoke. There's some differences. I mean, obviously, there's no nicotine in wood smoke. I dare say the world would be a different place if there was nicotine in wood smoke. But every one of these ones in italics are just examples of known carcinogenic or otherwise toxic materials, you know, on EPA's list and so on. Even such things as dioxin, you know, formaldehyde, benzene, and so forth that often people consider as industrial pollutants are actually the highest exposures in the world, and probably in these ancient settings. So I think it is fair to say a toxic waste factory. I'm not going to go through this, but we have lots of evidence now about the health effects from this. Sort of best evidence at the top, coming down on each side, mainly in women and children. The burden of disease estimates put indoor smoke from solid fuels as 10th among all major risk factors in the world, with malnutrition at the top and the HIV epidemic there and the tobacco epidemic. Indoor smoke from solid fuels is there. Roughly 1.6 million premature deaths a year. The unit here is Dalley's lost life years. This is what's used in international comparisons of risk factors. In developing countries, of course, it's higher up the list. Here's for India. Indoor smoke is third after underweight, you know, malnutrition, and unsafe water and sanitation as risk factors. Not a small part of the global health picture. Not the dominating part, but not a small part. This evidence is becoming more and more confirmed. This is a recent analysis some of us published, meta-analysis, systematic review and meta-analysis of pneumonia and indoor air pollution. And we are updating these meta-analyses for all the other diseases at this point. All right, well, so what is the issue, or what can we do about this? Well, here's a situation in China where we have very complicated energy picture. Susan Fisher was here, did her dissertation work in China. She knows this well. You've got this woman uses wood, she uses crop residues, she uses coal depending on the time of year, what she's cooking, how she's feeling, so forth. We had a contest last year, ended last year, to have improved biomass stoves that had very high combustion efficiency and therefore low emissions. And this is one of the winners of the stoves. This picture was actually taken Saturday, because I was in China on Saturday. And this is a device that has these, compared to the coal stove it's replacing in Shanxi province where we're working, the energy efficiency goes from 17 to 41%. The CO-CO2 ratio, which is the best indicator and simple indicator of combustion efficiency, is dramatically improved, and the particles per kilogram of fuel goes down dramatically as well. This also has a chimney, so any remaining material goes out of the house at least, although it still, of course, contributes to global warming. And it uses a blower. It's one of the ways it gets very good and stable combustion, takes advantage of the fact that almost all Chinese households have electricity. Just 18 watts, you know, $2 a year or less for the electricity. And our calculations in terms of the benefits, I won't go through this, can be illustrated here. This is the health cost effectiveness. This is kind of complicated, I'm sorry, but it's an important graph. These are log scales now. Health cost effectiveness, dollars per dollar. How much dollars does it cost to reduce one lost healthy life year? And then this is carbon cost effectiveness in international dollars and CO2 equivalents. And this is using just the standard global warming potentials for methane. Let's take this China wind project that we just took out of the literature there. You can see it's producing health at, $800,000 a dollar. It's you wouldn't propose this as a health measure. It's producing carbon benefits at, $70 a ton. Well, that's more expensive than the current carbon markets, but we could easily get there. At our household coal to biomass gasifier stoves, you can see down here our calculation is we can produce carbon health benefits at a few $100s a dollar, and carbon benefits of $5 or $6 a ton. These are very cost-effective under current thinking. This is roughly the cost-effective region in China, how much country at China's level of development should be spending on health, and how much the international voluntary carbon offsets are being sold for. If you go to the clean development mechanism, they're more expensive than this. So our argument is that this is a win-win deal. Co-benefits, here you can sell the carbon offsets to the Belgians or the French or the Canadians, or not to us yet, but maybe after January 20th, we'll be buying carbon offsets in the international market, and get these health benefits as well. In fact, we have our project is basically to pick off part of the cost of this technology, which is about $100 for these stoves, plus the program costs, to charge it to the Belgians. We are in negotiations, and I think we're going to get the government of China, actually the provincial government, to pick off about a third of the cost because of the health and other social benefits that they see of these devices, improved energy efficiency. And of course, households themselves should pay for some of it. It doesn't do any good to give people things. And they get a benefit, of course, they don't have to buy any more coal. These devices use corn cobs as their fuel input. They grow enough corn that they can do their entire, with these highly efficient devices, they can use their entire fuel supply in the form of corn cobs, don't have to buy coal. So this is our thought, and we're pushing forward to this. It's one of the constituents of these products of incomplete combustion, responsible for much burden of disease, not exactly the methane itself, but that associated with the incomplete combustion. So you have a double benefit in climate and health, and can be potentially done economically. Now, of course, I have a stake in a higher warming potential for methane because it makes these projects look more attractive. This is a very particularly attractive project because of it substituting for coal. But if you're just improving the efficiency of biomass, then you don't get the CO2 benefit because that's renewable in both cases. So you have to argue on these non-CO2 pollutants, methane, and of course the other one, big one, is black carbon. All right, methane and global equity. We have seen how how are methane emissions distributed? Here, I can go back to this graph, and I'm just going to take these top two things. This is the amount that's in the atmosphere today, basically 2005, let's say today. How is that, who put it there? How much of it is our responsibility as Americans or Chinese or whatever? And this is some work, and you've seen graphs like maps like this. This is from a paper we did a year ago. Jamesine Rogers, who's here, was a former student of mine, and we were co-authors on this. It was our database. It's a neat software. You can stick anything in here, chewing gum consumption or whatever, and it distorts the maps according to what you put in, and you can see the places in the world that release most of the CO2 are, well, Europe and the US. Japan is there. Sub-Saharan Africa is not much of a contributor here, even Latin America. But this only considers the CO2. And the ratio of the most emitting to the least emitting on a per capita basis is about 500 to 1. But what happens if you add methane to this picture? Well, here's another way of looking at it, and this is the distribution of emissions, the fraction of total CO2 in the air in the year 2005. The US has 21% of it. China is responsible for 8%. This is the operation of the Chinese economy up to the year 2005, taking into account that some of that CO2 has been depleted by natural processes. Other countries is 26, and I have not tried to, this is again, Jamesine Rogers and I are putting together another paper on this. We have not tried to distribute the land use changes to particular countries. That's very tricky, deforestation. So this is just fossil fuel and cement emissions. You've seen pictures like this before. I put Brazil here. It's only 0.8% because when you add methane, the picture changes. Here's the US emissions of methane, and you can see the landfills are very important, livestock, coal mining, oil and gas, a lot of low-hanging fruit here, even without trying to deal with the livestock issue. Here's India. It's a little bit different. Enteric fermentation from livestock and rice, together more than 50%, but even India has some leaks and waste, poorly managed waste. China, the same. All right, so here's that distribution, adding the methane to it. The US contribution goes from 21% to 17%. Brazil, which was 0.8%, goes way up to 2.4%. And the others shift. Basically, it evens the playing field a bit in terms of the impact on global warming, which of course has a political connotation. That big ratio between the rich and the poor there's still a ratio, but it's not quite as big anymore. Indeed, if you look at it on a per capita basis, here you have the methane, again, basically the amount of tons of CO2 equivalent in the atmosphere. So you and I have roughly 680 tons of CO2 in the atmosphere in our names right this very moment, CO2 equivalent. So that's your natural debt. That's how much you owe the world. In a sense, you've burdened the world with your activities. Now you say, well, I didn't do it, my grandparents did it. Well, but you accepted the freeways and the schools and everything else your grandparents built, so you have to accept the debt that goes along with it. I mean, that's the argument. So it's interesting, the US is the biggest one just in terms of CO2, but when you add methane, lo and behold, we get off the hook, and Australia becomes the biggest emitter in the world, although we're second. And the developing countries are still quite a bit smaller, but in a relative sense, they go up more because they have more methane emissions compared to their CO2. And indeed, the ratio that was 500 to 1 before goes down to about 40 to 1 from the highest to the lowest emitters. So it's still an inequitable world, but a somewhat different political picture than what's often portrayed if you just look at CO2. All right, so that's here I'm coming to the last of the subplots, different historical framework, and it sort of takes off on the previous one. Actually, when you think about it, why is it that we're only looking at the climate change and the emission of greenhouse gases as something that started happening in 1750? Sure, that's when major amounts of fossil fuels were being burned. But if we believe that land use change and agriculture and so on were producing CO2 and methane since 1750, they must have also been producing it before 1750. And there's a guy named Bill Rudiman who has been writing on this, a very reputable climate scientist. I don't know why his stuff hasn't seemed to hit more. I recommend, he's got a great book called Plows, Plagues, and Petroleum. So his argument is that I'll show you, his argument basically is that if you look at the last 10 ice ages, there was a decline at the end of the ice age of CO2 and methane emissions in the atmosphere. And the evidence of this is true. But that decline was reversed, not in 1750, But thousands of years ago, with the invention of agriculture and the clearing of land and the development of irrigated agriculture because of methane and CO2 emissions, and I'll show you. Certainly it's risen, the rate has risen dramatically since 1750. But in fact, here's the book, Plows, Plagues, and Petroleum, Princeton University Press. He's also published a lot in climatic change and other places. Here's basically the idea, is that here's the methane trend since the last ice age. And instead of following what it should have followed based on previous ice ages, it actually started reversing about 5,000 years ago. In terms of CO2, it reversed about 8,000 years ago. Started up again. This, of course, coincides with the development of agriculture overall and the clearing of large amounts of land around the world for agriculture. And this coincides with the invention of irrigated agriculture, first in Southeast Asia and elsewhere. So basically he's saying that the amount that we've added to the atmosphere, human activity is added to the atmosphere, is not what we've seen since 1750, but what it would have been if you go now, an extra 40 ppm for CO2 and an extra 250 ppb for methane. I won't go through his argument about that. It's very interesting arguments. Why the plagues in his title? Because he associates the changes in the global climate in the Middle Ages, the Little Ice Age, with the great plagues that knocked down agriculture, the Spanish coming to the New World that killed off 95% of the Native American population, thereby stopping the deforestation that was going on. The peak of deforestation in the U.S., in the North American continent, was about the year 1500, based on charcoal deposits in offshore and so forth. So he says basically we have 150 gigatons of carbon in this industrial hair, he calls it, the very rapid rise. And of course that's on its way to being much, much larger. But that was preceded by a 300 gigaton pre-industrial tortoise that in fact added more initially. Now it doesn't change any of the need to do something about climate change today, or the sensitivities of the climate to greenhouse gases or anything. But it does change the historical context here. And it basically brings back to the table the issue that part of it is just human impact on the planet. Land use change, agriculture, and so on. Fossil fuel is a particularly nasty version of it, but it's by no means the only part of it. And of course, it raises, it does change the context of it, but doesn't actually change what ARB might want to do in terms of doing something with it. All right, so I'm going to finish up here, but remind you, carbon dioxide is important. However, these are the laws called Carbon-thermodynamics. First one is keep all fossil and forest carbon out of the atmosphere of any sort, any type of carbon. That's the law number one. But if you can't do so, the least damaging form to release it is CO2. CO2 is non-toxic, any kind of level we're likely to reach. And it's got the lowest global warming potential of anything. Most of the things you put in the atmosphere turn to CO2, first of all. And in the meantime, have higher warming potentials. And even renewable, non-fossil carbon, like from animal dung, is damaging for climate if not released as carbon dioxide, if it's released as methane. So those are my three laws of carbon thermodynamics. And of course, incomplete combustion is a major component of what's happening to the atmosphere. Methane, CO, non-volatile organic compounds, non-methane volatile organic compounds, black carbon, organic carbon, and so on. And then they've got the NOx and the SO2. Incomplete, poor combustion, poorly managed combustion is actually the major part of the problem. Those actually add up to more than the CO2. CO2, you might say, is well-managed combustion. Maybe you want to avoid combustion entirely. But nevertheless, it's better than the poorly managed combustion. So I developed the ranking of carbon emissions, the pharmaceutical index. Showed this to Al Gore. He liked it. That's the title of my talk, came from it. So carbon dioxide is noxious if fossil or forest derived, but benign if from renewable resources. Products of incomplete combustion, such as carbon monoxide and hydrocarbons, are like CO2 on caffeine. They're several times worse. The global warming potential depends on who estimates them, 4 to 8, something like that. Methane from any source is like CO2 on steroids. dozens of times worse, you know, at least 21 times worse, but maybe 72 times worse, something in that range of depending on how your time perspective. And of course, black carbon in particles from incomplete combustion is like CO2 on crack. It's hundreds of times worse. So, conclusion. Methane emissions are more important than current official weighting factors indicate. Perhaps. May well increase in value, if you will, and they're in the post-Kyoto deliberations now starting. Developing countries have a bigger role. Methane is emitted as part of poor combustion, which also produces much health-damaging pollution, contributes to global tropospheric ozone. Proving combustions offers substantial greenhouse as well as health benefits in a cost-effective way. Ways to control are quite different than CO2. It may be easier for many of these things, like as I mentioned. Fixing leaks in natural gas pipelines doesn't affect my lifestyle much. I might pay a little more for the natural gas, but it's not like having to change your complete lifestyle. Now, reducing meat consumption, which is a big part of, and dairy consumption, which is part of the methane picture, that's a bit more difficult. Maybe easier in the short term. So bottom lines, way to reduce warming in the next generation is to put more attention on methane and the other shorter-lived pollutants. We use greenhouse gases, but of course some of them aren't gases like black carbon. Once the heat enters the Earth's system, it does not matter where it came from. Earth doesn't care whether that joule of energy came from methane or CO2 or black carbon or whatever. It is causing the problem. And this is a very important issue. For some types of impacts, it's the rate that's important, not the amount. Now, for some types of impacts, it's basically the total integrated heat coming into the atmosphere, sea level rise, for example. But for many types of impacts on ecosystems, many impacts on many human systems, adaptation, you have to give time for adaptation to occur. And so the rate is very important. So you really need to think about perhaps, actually, I was at a meeting just recently in China where there was discussions about actually having a basket of global warming potentials, if you will, or weighting factors for rate, for pollutants that affect rate, and another basket for those that affect the integrated amount. And of course, CO2 is the big one on the integrated amount. Methane actually sits a little in both because with a 12-year e-folding time, it lasts a lot longer than many of the other shorter-lived things, but it sits in both camps. And this, I think, will be one of the proposals looking at the two things. And of course, certain types of impacts in California are going to be affected mainly by rate. Others, are going to be sort of a victim of integrated absorption of heat. The only way to slow rate in the short term is to reduce greenhouse gas, is to reduce methane and other short-lived components. And of course, while working to deal with CO2 in the long run, has to deal with CO2 if you're going to treat this seriously. So, finally, carbon dioxide is still important, but do you know your methane footprint? And I've tried to find a nice calculator somewhere on a website to give me my methane footprint. I haven't found a good one. Maybe somebody knows of one, because people don't think about it much. But here's the California, preliminary estimates of the California emission pattern. Probably experts in this room can tell us more about it. And I note enteric fermentation, that's basically cows and sheep. Because of the intrinsic nature of their digestion, this isn't easy to slow down. I mean, as long as people are having dairy and eating the meats. People have tried to change it with the different types of feed and genetic modifications without much success yet. But look at this big impact from manure. That's poorly managed manure. If that's accurate, and I can't vouch for that, just off the CARB website, that's a significant potential low-hanging fruit for the state. In addition, landfills, wastewater, and oil and leakage from the oil and gas industry. So again, I'm not an expert on this. I'm just showing you the big numbers, but it does raise the question about whether might want to look at these low-hanging fruit, while, of course, dealing with the very thorny issues of CO2 in control in the long run. Bill Nazaroff, a colleague of mine at Berkeley, who many of you probably know, has a homework problem in one of his courses where he actually has them calculate how much gas could be leaking out of California homes, natural gas could be leaking out of California homes, and people not smell it. Now, they put an odorant in But they put that odorant in based on the threshold of the human nose, but also based on prevention of fires and explosions. But they don't worry about small leakage. I mean, so turns out every house in California could be having half a kilogram a day of leakage, and nobody would know it. Now, I'm not saying that's happening, but if you take that nationally, we could triple our national methane emissions and nobody would know. So, I mean, there's a simple, I don't know if this is practical or not, but doubling or, putting more odorant in natural gas, it costs almost nothing, it has almost no political impact. Of course, people would require people or PG&E or somebody to go repair people's gas pipelines a little earlier. Might be a quite cost-effective way of dealing with this. So, I put my presentations on my website, and I have many publications there. And thank you very much. Okay.
Yeah.
Go ahead.
Chuck White with Waste Management. I'm curious about the current time frame that is used for estimating the relative global warming potentials, which is the 100-year time frame. And you've kind of indicated that the IPCC or Kyoto whatever comes after Kyoto may, in fact, revisit that. What's your thinking on how that could potentially work? If there's a different time frame window, different 100 years, would that be the same window for all gases, or would there be a different window for methane versus a different window for CO2? And how does that work if all of the different gases are operating under a different window?
Well, in fact, that's the problem now. Using a 100-year time frame actually treats each gas differently.
Right.
And this really people haven't pointed this out much. I mean, if you think about it, it's a very strange formulation that we would care equally about everything out to 100 years and then care nothing about the year 101. Whatever our, forward-looking thing, it's not related to how many fingers we have. I mean, 10 times 10. It's not a step function. It's a smooth function. And what is a smooth function that decreases over time? It's it's a discount rate. Now, I'm told, I wasn't there, I wasn't in that version of IPCC, but at the time they developed this, and I've talked to people who were there were no economists on the group. Economists, think in that way, and the physical scientists who were there were uncomfortable with the application of discount rates, but they recognized you had to do something about time, so they established these time. And they said, well, we'll calculate for 20 years, and we'll calculate for 100 years, and they also have a 500-year one that they publish. And then, of course, I have a cynical colleague who said when it came around to Kyoto, they said, well, it was the Goldilocks thing. It's a little bit too hot and a little bit too cold. One seemed too short, one seemed too long. We'll take 100 years. I mean, it's not actually too far. That's, how it happened. But the trouble is one trouble is it treats the different gases differently. Because a discount rate would treat them all equally. And I just converted the methane CO2 numbers to equivalent discount rates, and you could do that with the N2O and the other gases too. But even better, it would be to establish a discount rate. But of course, even the name discount rate raises red flags in some quarters, and so I wouldn't be surprised they end up sticking with time horizons. But they may, I would say, based on this recent meeting I was at, what people are thinking is that they have a separate time horizons for rate important gases and another for integrated gases. They might stick with 100 years. But this isn't the place to get into it. There are a number of rather perverse things that happen when you use this time horizon in these kinds of calculations. And maybe again back in 1994 when the world was first learning about this stuff, it didn't matter so much. But now we're proposing to spend trillions of dollars. It's time to get these things as right as we can. Now there's another, if you look in the literature, where people say, well, anyway, warming isn't the right thing to use. We should use actual temperature rise. So that should be the unit. And then other people say, well, we shouldn't use actual temperature rise. We should use actual impacts. Wait till nasty things actually start happening, and use that as the as the metric, not warming. And you can see the value. The problem with that is, anytime you move the next step down the causal pathway, you have to bring in global climate models and impact models and differential adaptation in different parts of the world. I mean, you never agree on it. So there's some value. I mean, after all, just think about how we set air pollution standards. We set an air pollution standard, for every city in California. We don't look at the differential age distribution in cities in California and say, oh, well, this place has got a bunch of healthy people who don't have to worry about air pollution. We're going to let, Vallejo have a higher level. We don't look at adaptation measures. We don't look at the indoor-outdoor relationships. We just set a uniform level. And so the argument is, for policy, it's not necessarily an advantage to go all the way down the line and calculate the differential impacts. And then there's the political side of it. Would you actually ever be able to set something differently in different places? I mean, even if you knew, no, probably not. The policy has a different set of obligations and demands on it than the science. So I think they're probably going to stick with something like global warming potentials, but I think they're going to have to address at least, obviously the black carbon thing is the pollutant of the month. And it's very powerful but very short-lived. It's the methane problem, to another order of magnitude. And I don't think the IPCC, at least the scientific group, is ever going to come up with a global warming potential for black carbon. How can they? It's not global. But, it lasts a week. Can't be global. Methane, at least, is perfectly mixed, lasts long enough to be mixed. But all the other, the really short-lived stuff, like black carbon, doesn't. So it's warming locally. And that air that it warms may, spread globally, but it's a quite different thing. But this is a big, set of issues that are coming up. So I can't predict how they're going to go. But some of us are saying that we at least ought to get away from this strange step function nature of the time horizons that treat the gases differently, end up treating them differently.
Two questions. First, on methane, it's not regulated as a reactive gas, so it's considered not to result in ozone. So my question is, what is the ozone potential as far as what percent does methane contribute to the ozone problems on a
well, I can
worldwide
refer
basis?
to the papers. I mean, globally, and again, not necessarily in Los Angeles or Houston or Beijing, but globally, the regional background ozone levels are driven by methane emissions. And then those factors, there's some nice papers I can send you copies of if you like, and that I'd rather not, I just figure trying to remember what they say. But it's very important. And also, what was striking to me was the cost effectiveness of control of this background ozone level is highest with methane reductions as opposed to NOx reductions.
So you're from the perspective of cooking, basically. The methane emissions from that is such that it's fairly easy to control that to reduce that methane.
Well, any methane, it wouldn't matter. I mean, methane from cows or methane from landfills, it's all the same.
Okay. The second question is on CO2. You mentioned that it's essentially permanent once it's in the atmosphere. It's so slow to be, I guess, sequestered geologically is probably the term. And that's where my question is, because we're talking about strategies to increase sequestration either in the soil or in biomass. So wouldn't that affect the longevity of CO2 in the atmosphere?
Well, yes, you're right. And if you started like charcoal, this stuff where they're putting charcoal in the soil and this kind of thing on a very large scale, it probably would affect those compartments. But this is the entire planet we're talking about with these compartments. It's a long time we're going to perturb those compartments very much by human activities. I think that's the answer. But yes, you're right. In principle, you would.
In terms of policy,
Wait just one moment. The people on the webcast maybe you could introduce yourself.
yes, my name is Reza Madavi. I'm an economist with the research division. In terms of policy, based on your discussion, I get the impression that to reach our target in 2020, we should be putting much of our effort in reducing methane in California rather than CO2 emissions, which basically currently we are doing.
Well, I mean, I come from the fortunate advantage of being not very well informed about exactly what the policy is, so I can't criticize it. I'm saying that it ought to be considered in any policy, exactly the trade-off here. But I can't tell you, I think California is controlling methane, at least in terms using the factor of 21, like that's in its inventories, I assume. Methane controls count as part of their, must be an expert here on this. Yes, definitely. So the factor of 21 is driving, some changes. I went to a really interesting meeting in Beijing not too long ago called Methane to Markets thing. And there was 1,000 people at this meeting, 2 academics, no NGOs, oil company executives arriving in limousines, the minister, the American ambassador, Bechtel, big instrument manufacturers, satellite companies, all driven by the factor of 21. And the fact that if you stop methane leaks in the oil and gas industry, you can sell more natural gas. So that's driven by those 2 things. But there are landfill people there, dairy people. Consulting companies wanted to make money on this. Companies selling gadgets to measure methane, cameras, you could see it. A Japanese satellite company that you can now buy time on their satellite to measure methane from space. Your leaks on your pipeline from space. They say they can measure 4 ppb at ground level from space. This is driven by the factor of 21. You had a factor of 48 or whatever, you would just have a lot more of that. I mean, so it's not as if nothing is happening. I'm just saying that given the world we live in and the fact that that we need to have some control over the rate of warming as well as the total amount, that perhaps a bit too much attention, in a relative sense. In addition, as you know, CO2 is very intractable. I've got this, I was waiting for this, a question like this. This is, did you ever see the movie Aliens 2? Where this is the terraforming unit that they put on a planet in order to create greenhouse gases, in order to warm the planet. Well, we might need a terra-reforming activities of various kinds. Now, these may be charcoal in the soil, or maybe growing forests, or they may actually be big machines like this. There's this whole industry of growing air capture, they call it, of CO2 and sequestration. To deal with CO2, given what's happening around the world in terms of energy use and how little we've done so far, it may take some very draconian things. In the meantime, shouldn't we be getting rid of the low-hanging fruit that really will change? I mean, I'm trying to think of an analogy. When you're driving to the drugstore to get your blood pressure medicine, you should wear your seatbelt. Yeah.
Great. Okay, what we'd like to do is take a few of the questions. We'll come back to, like to take a few of the questions from the webcast participants. And Dr. Smith, I'm going to give you these 3. You might want to, I think they're in a good order, but you can rearrange them if you prefer. And then we do have a couple more.
So this is an explanation. Asked for why methane contributes to ozone formation on a global scale rather than a local scale. Of course, it contributes everywhere. It's just much more important globally. And I don't want to pretend to be an expert on this chemistry, and I'm glad to refer people, or I can put on the website or whatever. Since there's so much expert work on this, rather than myself get into it, but it contributes on a local scale too. Yeah, I was under the impression that the reason I look at non-methane organics and ozone formation because methane has a small impact. No, it's not. It's not the case, at least in the modern work that's done. And there's rather a large amount of this work in the atmospheric chemistry literature. You say at the outset you're not going to talk about Arctic methane, but recent reports seem to indicate its potential dwarfs the sources you discussed. Well, of course, that's a big risk. All right, and but I don't think it obviates anything I've said. We still have to deal with the stuff we can deal with. I mean, somebody asked a question, I gave a talk like this at Berkeley not too long ago, and somebody asked an interesting question, a hypothetical question that I'll reframe slightly. And basically is, let's say the groups that study in the Arctic, every summer, and they come back and they look at their data and they email each other and they decide they need to have an international combined press conference, and they say, we've decided, that there's a 95% certainty that runaway methane emissions have started from the Arctic tundra or something like this, and the planet has to deal with it. Well, what would we do? What would the world do? I don't think CO2 would play into that, what we would do issue very much. We would, of course, be doing as much adaptation as we could in those parts of the world that are particularly vulnerable. We'd be probably looking at geoengineering and putting sulfates into the stratosphere, maybe spraying clouds, ice crystal to make clouds or something. And we'd be really working on short-term pollutants, like methane, black carbon, and so on. Or another scenario, that one isn't actually too far-fetched. Didn't happen this year, but could happen one year. What if they came back and said, we've looked at it, and runaway melting is starting in the Greenland ice cap, and we're going to have 7 meters of sea level rise in 30 years. What would the world do? CO2 wouldn't play into this at all. And so, if you think you just change it, just the time frame a bit, all of a sudden, things come look a little differently. Now, when I mentioned this, that I gave this presentation at a small meeting with Al Gore, and got a lot of pushback. And I got a bit of this in other presentations I've made. Hasn't happened here yet, but and that is, and that's why I put in, I dispersed in this, CO2 is important. CO2 clearly is important. And I think Al Gore's concern was, it didn't have any, I don't think, concern about sort of the scientific message, but was the political message. It's hard enough to get people to think about CO2, and if you can confuse them with methane or presumably black carbon and other things, it just diffuses the methane message and maybe provides chinks in the armor for special interest groups to get in there. But it seems to me that we've reached a stage in which we have to be pretty careful in what we do, because we're spending pretending to spend lots of money and planning to spend lots of money and actually want to accomplish something with it, and we better be sure we're getting what we pay for. But again, I'm not. I follow some of the science news that comes out about the Arctic methane emissions, but I'm not an expert.
Marc Vessier, Air Resources Board. Now, I was wondering what you know about the role of wood smoke in California in terms of health effects, and whether you have any idea if using EPA-certified wood-burning devices is something that we should look at differently, based on what you said about the cooking.
And sorry, I remember I had one of these slides I just referred to, not my work. This, again, is Jason West at the University of North Carolina, looking at the cost-effectiveness of reducing the various components of ozone creation, and you can see the highest cost-effectiveness is in methane reduction. I can refer people to the articles. Yeah, well, wood smoke, actually I don't think I have that graph here, but just taking the CARB website, what do you suppose the biggest source of, of course, I've given away the answer now, but the biggest source of particles, primary PM 2.5 emissions is in the state? Well, it's biomass combustion, wood, residential wood combustion, but also agricultural and controlled forest fires and so on. Now, of course, it's not in the middle of cities where people are, so in general, well, not quite so true with residential combustion, but nevertheless. So the intake fraction, the fraction that reaches people and people breathe in, is lower than perhaps with the average vehicle or something like that. And partly it's because California has had great success at lowering the emissions of industrial sources and transport. And so what's left is what's not been controlled much is residential wood use and agricultural burning. In fact, it's a very interesting thing if you look at this broadly. You usually think of some people think of emissions being associated with industrialization. Well, yes, but of course very poor countries don't have much in the way of emissions from fossil fuels, and very rich countries have controlled them substantially, and middle-income countries tend to have a lot, like China, India, and so on. So fossil fuels tend to go what's sometimes called the Kuznets environmental curve, just for emissions. But what about biomass? Well, it's very interesting. The biomass use per capita is almost the same. There's almost no relationship. It's not the same. It's almost no relationship with income. It's almost entirely a function of availability. So there's not much biomass use in Singapore, but there's a lot in Finland, even though they have the same in terms of wood. In terms of crop residues, it's not related to income. It's related to the crops you grow. So in India, they grow a lot of crops. They might burn the residues in their houses for cooking. Here, we burn them in the fields. We don't burn them in our houses. But the amount of burning is actually quite similar, and it's basically only a function of what agriculture there is. Now, I understand Europe, and to some extent California, is trying to control its agricultural emissions by various things. It's not easy to do, of course. You can't tell people not to burn because there's not much else to do with it. It's expensive in energy using to collect it and do something else with it. But this is an interesting issue. But I think probably you were getting at, we did this review. I showed some results of it on the toxicology of wood smoke. And basically and this was also about the same time that the WHO did a big review of for the particle air pollution standards or guidelines from WHO. And the conclusion was similar in both cases, which was there's really pretty good evidence that the respiratory effects of wood particles are very similar to those average urban outdoor air pollution, which is a mixture of biomass and fossil fuel and other things. But that the evidence on cardiovascular effects is weak. Doesn't mean it's not the same, but you can't really make a conclusion. So one of the recommendations is that more work needs to be done on epi and tox related to fresh biomass particles and cardiovascular outcomes. And if I had to guess, if I was forced to guess, I would say the slope is lower. That is, the effect on cardiovascular impacts is lower, is shallower for biomass particles than fossil particles. But there really isn't enough evidence yet. We are doing some studies on heart disease and wood smoke in the third world, which will help add to that database. But it's hard to do that kind of work in the first world because, well, you know the reasons. I mean, there aren't too many places where you have pure biomass smoke in large populations of the type that you do outdoor epi studies in. And maybe somebody knows of one, but I think there's some evidence from New Zealand and other places that does seem to show that biomass smoke has a somewhat less impact per unit exposure for cardiovascular outcomes, but not for respiratory outcomes. But whether you would ever have a policy that you would say, here in San Luis Obispo, you've got 80% biomass particles 40% of the year, and therefore you get a higher air quality standard. I'm not sure that you could ever, from a policy standpoint, that you would ever be in that position to justify that. When combusting methane from dairy lagoons or landfills, the carbon dioxide is released is considered to be biogenic by most protocols. Is this accurate? I think so, yes. I mean, presumably those aren't fossil cows that produce the fossil dung that went into the... So, and they're not eating coal, so I think that's fair, yes. Can you go through the chemistry of methane oxidized into CO2? Well, okay. I think I did that at the beginning, but let's see. Anyway, methane, it's got one carbon and 4 hydrogens, and the hydrogens go off to water. That's the question is what happens to the H? They go off to water. You get CO2 in water. So you get two oxygen molecules, which each have 2 oxygens, plus the methane. Get 2 hydrogen water molecules and CO2. This person wants the references if I can send it to him. I do, yes. Yeah, Hal, who's an old friend, thank you, Hal, I must be listening. He's got one of these references I was referring to right here. So this is Linking Ozone Pollution and Climate Change, the Case for Controlling Methane by Fior et al. It's a report out of EPA. But there are plenty of journal articles as well.
Yeah, in discussing these near-term pollutants, there's clearly a trade-off. If we reduce agricultural burning and try to force soil incorporation or mulching or something like that, we're going to get both more methane and more nitrous oxide.
Right.
So what would you suggest as a strategy to address that trade-off?
Think about it carefully. Right. And do that, and get the numbers right, because a lot of these things, aren't so, there's some counterintuitive results that you get, and you may end up being not where you want to be. I can't answer, right off. Obviously, if you just put pure charcoal in the soil, it's not going to produce much at all, and that's a great thing. Presumably, more or less okay for the soil as long as you don't put too much in it. It's not going to decay to any methane if it's charcoal. But
where would you get the charcoal?
Well, that's right. How would you get the charcoal without producing a lot of other nasty stuff in the same time? That's good. That's right. So life cycle analysis clearly is, you guys are experts at all this. So. Yeah. Mm. Right. Yeah, that might not be a good trade-off. If you're going to, better to put the stuff into CO2, much better. Even at 21, it's a lot better to put it into CO2 and to let them. This is a problem with the, biogas as well. Not sort of industrial scale biogas like at sewage plants in this country or dairy farms or something, but small household scale biogas of the kind that's used in the third world, which is a great energy source from most perspectives. It's renewable. You retain the fertilizer value of the dung. You can provide some human, sterilization of human waste. It's clean when it's burned because you can premix the gas with the air and get very clean burning, but it doesn't take much leakage of methane from that biogas system to make it a net greenhouse producer. And roughly 5% at 21. So this is tricky with these small-scale systems that might have leaks. You can easily imagine 5% leaking from a household biogas plant out in the middle of China.
Bart, did you want to say anything or have any questions? Great. I agree. I think we all want to thank Dr. Smith very much for coming today. Give him a big hand. And I'm sure if you have any follow-up questions, just let us know. He'll be glad to respond as he has time in the future. So thank you very much.
Sure.
And I think we got all the questions. We might get a few more later.
Yeah. Mm-hmm.
This chart here, what are the units on the left-hand side?
Just relative warming, 100.
Relative.